Alright, so in this video I'm going to talk to you about some compound measures, okay, involving rates of change. And the first one is about average speed, distance and time taken, okay. So here's the equation that we often use. Average speed is the distance divided by the time. Now if you want to remember this as a handy triangle, you can do. The idea is that you just got to remember to put the D, S and T there, and you can rearrange this equation quite simply in your head by just covering up the letter of the compound measure you're trying to find. So in this example, if you are trying to find the average speed, you cover up the S and you can see it's D over T, distance over time. If you wanted to work out the distance travelled, you cover up the D and then you've got the product S multiplied by T. Can you see you can rearrange this equation to make it distance equals average speed times time, okay? And finally, if you want to work out the time taken, you cover up the T and you've got D divided by S. So rearrange this equation, you've got time is going to be equal to distance divided by the average speed. Okay. Let me give a simple example of how this works. Okay. So imagine, let's do it where I want to work out an average speed. So imagine we travel a distance of, say, 150 kilometres. Okay. And imagine that the time taken to do this is, doesn't have to be difficult, okay? Let's just say it's 5 hours. Okay, so 5 hours. So it might be that you're driving a car, okay, and it takes you 5 hours to get there. Now just remember, we're trying to find an average speed, okay? Because realistically in your journey, you start, you build your speed up, you stop, slow down depending on traffic, what kind of town you're in, whether you're on the motorway, highway, freeway, autobahn, whatever you want to call it, okay? A high-speed road, okay? You're not travelling at the same speed all the way along, but from the start to the end of the journey, we're talking about an average speed. In general, if you were to start from the beginning and end at the end, how fast would you theoretically have to travel throughout, okay, and maintain that speed? That's what an average speed actually is, okay? So we don't actually just say what is your speed, we tend to say what is your average speed. The word average is pretty important there, as I'm sure you can imagine, okay? Well, it's quite simple. You just do the distance divided by the time taken. So in this case, the distance travelled is 150 kilometres and the time taken is 5 hours. I've given you a nice simple one. 150 divided by 5, that is 30. And then you just put in the units. The units are quite simple, okay? It's whatever units we're using for distance divided by whatever units we're using for time. And for distance we're using kilometres, and for the time we're using hours, so it's kilometres per hour, written like that. So that is your average speed, okay? Pretty slow actually, but yeah, there you go. Could be a cyclist, okay? Could be someone from the Tour de France, I don't know. Anyway, so that's that. Sometimes you're asked to write down what the answer would be, for example, in metres per second. So can we convert that into metres per second? Okay. Yes, of course we can. We can convert that into metres per second. So what we're going to do is we're going to look at 30 kilometres per hour. First of all, convert it into metres. Okay. So we're going to take 30 kilometres and we're going to convert that into metres. So that will be 30,000 metres. Okay. Remember your conversions from my previous video I showed you with the kilometres and the metres, yeah. And then we want to convert the hours into seconds, okay? So we need to know that 1 hour, okay? We need to know what that is in terms of seconds. Well, 1 hour is 60 minutes, as I'm sure you're aware, and 60 seconds in 60 minutes means you've got 60 multiplied by 60, so that means you've got 3,600 seconds in 1 hour. Okay, so if we're going to do our conversion, okay, we've got to look at 30 kilometres being 30,000 metres, and we're going to look at each hour being 3,600 seconds. Okay, so I think we're ready to do this now. Let me just rub this off and put my answer up there so you don't get confused with me writing up here now. I'll just write in a different colour. Okay, so it's a 30 kilometres per hour is the same as 30, whatever it was, 1,000 metres, and that's per, don't forget, that's per 1 hour, so per 3,600 seconds. Okay, and then we just work out what that is. This is where you get your calculator out and just type it in. So 30,000 divided by 3,600. Okay, and that's given me 8 1/3. Okay, so it's 8 1/3, and then the units are meters per second. Okay, and that is it. Okay, that's your simple example. Okay, another question might be, maybe we're given the time and the average speed, we're going to work out a distance. Okay, I'll just fill you in with one of those examples. Okay, let's just rub this all off now. So let's just suppose that in my next example we are given an average speed. Okay, and this time I'm going to say that the average speed is, say, 5 meters per second, because we're talking about a runner possibly, or a jogger. Okay, so I might consider that fast running speed, so I might consider it a normal jogging speed, whatever, it's 5 meters per second. And let's just say that the time taken, okay, is, let's just suppose that they're out running for 1 hour. Okay, and what we're going to do is we're going to work out what the distance travelled is in that time. Okay, that's it. So what you do is you think, right, okay, distance is average speed multiplied by time as your equation. Okay, so average speed multiplied by time. So you want to do 5 multiplied by 1, but check the units. Okay, you want to be able to be consistent with the units. That's in meters per second, that's in 1 hour. Okay, it'd be more convenient if that was in meters per hour or kilometers per hour. Okay, so the thing to do is change one of them. Usually it's a bit more fiddly to change that one because it's a product, well, not a product, it's a quotient of meters and seconds. Okay, usually it's easier to change that one. So we convert the 1 hour into seconds. Do you remember how many seconds that was? 3,600. Okay, so that's 3,600. I'm going to put a little less there for seconds. Okay, and then it's easier to do, you see. So basically 5 meters per second means you do 5 meters every second, and if you're running for 3,600 seconds, you're going to do 3,600 times by 5, aren't you? So 5 multiplied by 3,600. Okay, and then again use your calculator and work out what that gives you. So 5 multiplied by 3,600. Okay, that gives me 18,000. And then just check what the units are. So meters, okay, because it's meters per second, 18,000 meters. Sometimes it's more convenient to write it in kilometers. This is why knowing your conversions is useful, because if this is a real world example, someone is running at 5 meters per second for 1 hour. Quite, plausible really, isn't it? Someone might go up for 1 hour at 5 meters per second, okay? Then you'd calculate that they've done 18,000 meters, okay? But the most appropriate answer to give in this case would be 18 kilometers, wouldn't it? If someone's running with one of those, whatever it's called, Fitbits, or they're using Strava, whatever it is, okay, they're more interested in how many kilometers that they're running, to be honest. I've run it like this, okay, and 18 kilometers is more appropriate, okay. Well, I'm hoping you found those examples useful, okay. I'll see you again. Okay, I'm going to talk to you about density, mass and volume now, all right? So what do we mean by density? What do we mean by density? Well, it can be defined by using the equation relating density, mass and volume. It is the amount of mass that you have in an object per unit of volume that it takes up, okay? Let me give you a simple example. If I were to give you 2 diagrams showing you 2 forest areas, and imagine that the area of forest is exactly the same. If I've got, just say, 3 trees here in one forest, and I've got many more trees in this forest, or if you want I can exaggerate, imagine I cover that whole thing, which would you say is the most dense forest? Okay, hopefully you'd say this one is more dense. Why? Because there are more trees in it, but not just about the number of trees, there's more tree per unit area. Okay, now imagine these were populations in 2 similarly sized towns. Imagine that is town 1, town 2, okay? And imagine this is a population per traditionally square kilometre, okay? So imagine you've got 3 people per square kilometre, and here you've got 1, 2, 3, 4, 5, 6, 7, 8 people per square kilometre. that's the town with the densest population. Okay, so that's about population density. So the whole things, they all essentially link into this idea of density. And in terms of objects, okay, we look at the mass of an object, either in kilograms or grams, and we look at the volume that the object takes up, either in cubic centimetres or in cubic metres. Okay, and the relationship is that the density is mass divided by volume. Now, just with these speed distance time formulae, we can look at a triangle relating density, mass and volume, and here it is. Okay, the idea is that you cover up the one you're trying to find. So in this example, if you want to work out a density, cover that up, mass divided by volume, just like the formula there. If you want to work out the mass, and you're given the other two, you do density multiplied by volume. You can see the volume can be brought over to there, mass is density times by volume. And finally, if you want to work out the volume, cover up that, mass divided by density. You can see that if you switch these over, the mass divided by density gives you the volume. Okay, so that's what density is all about. Let me give you a simple example. Okay, in density. Okay, so what I'm going to do is I'm going to draw two separate objects. I'm going to make them cuboids because it's nice and simple. Okay, so there we go, and they don't necessarily have to be the same size, because that would just be too easy. Okay, this is GCSE Maths. It's got to be a little bit more challenging than that. Now, I could give you the measurements and say work out the volume yourself. I'm sure you could do that. Okay, length times width times breadth in each case, and you can work out the volume. So what I just pretend I've done that, and we've got the answers already. Okay, so this one here, I'm going to call that 5 meters cubed. And this one here, I'm going to call that, say, doesn't really matter to be honest, 9 meters cubed. Okay, I'll give you the mass of each object as well. Okay, so I'm going to say that the mass of this object is, for example, what could it be? Let's just say it's 20 kilograms. Okay, which is quite light if you think about it, because 5 cubic meters is quite a lot. Okay, and then the mass of this object. Okay, what can I call this? I don't know. Let's just call it 200 kilograms, just because it's convenient. Okay, what I want you to do is find out which object is the most dense. Okay, which object is most dense. Okay, what you do is you work out the density of each one. So for this one, D for density, you do the mass divided by the volume, and so you've got 20 kilograms divided by the volume, 5. It's actually quite simple in the end, isn't it? So 4. Now the units for this is a bit like the speed, distance and time. You've got the mass units divided by the volume units, and because I'm using kilograms for mass and cubic meters for volume, it's 4 kilograms per cubic meter. Okay. Now the thing is, when you're comparing densities, you've got to be using the same units. All right. So if this was given to you in, say, millimeters cubed or centimeters cubed, you'd have to convert it into meters cubed. Okay. Just so you can compare the answers. Same with this. If this was given to you in grams, you convert it into kilograms. Okay. So basically, when you're doing comparisons, you have to be using the same units, and make sure you convert them before you find the density of each. Right. This one, density, is going to be equal to mass, which is 200, divided by the volume, which is 9, and let's just use our calculator for that, shall we? Okay, so 200 divided by 9, okay, and that's 22.2 recurring, okay, and the units there are kilograms per meters cubed, okay. Now you might have been able to spot it before I actually set the question, okay, because this one I deliberately made a fair bit heavier than that one, okay, but you can see in terms of the mathematical calculation we did why this one is most dense, okay. It's because per cubic metre the mass of this is 22.2 kilograms, whereas this object here, per cubic metre, the mass is only 4 kilograms, so a fair bit lighter, okay. But that's how you do a conversion, okay? And that's how you'd compare the two densities of those, okay? I'm hoping you found that quite straightforward. I'm hoping you found that useful. Okay, I've got another example for you with density, mass and volume. So here I've drawn out a cuboid, it's supposed to be a cuboid anyway, with dimensions 4 centimetres, 12 centimetres, 10 centimetres, and it's made up of a particular material. Doesn't really matter what it is, wood, metal, whatever, okay, but it's made up of the same material, and the material has got a density of 0.6 grams per cubic centimetre. Okay, so one of the purposes of this example is because this time we're going to work out the mass, and also another reason is because I've used a different unit of measurement. Okay, so as I mentioned before, with density it's either in terms of meters cubed and kilograms, in which case you'd write a unit as kilograms per meter cubed, or it's to do with centimeters cubed and grams. Okay, so those are the two units of measurement we use for density, okay, nothing else. So the first thing to check is that make sure that all the units are appropriate, okay, they're all consistent. So we've got grams, centimetres cubed there, these are centimetres, okay. So the idea is if these were given in metres, say, but it said per centimetre cubed there, the first thing you do is convert all of those into centimetres to make sure they all match up. But it's fine, we're all ready to go. So to find the mass, cover that one up, density times by volume. Or just rearrange this formula, mass is density times by volume, okay? So we're going to do volume of this multiplied by the density. Now note the density is 0.6, okay? But the volume, we just need to work that out. That's quite simple, isn't it? So you just do 4 multiplied by 12 multiplied by 10. 4 times 12 by 10. Okay, and that gives us the volume of the cuboid. That's quite easy. You can do that one without a calculator. So that's 48 times by 10. So it's 480. Okay, 480. Or you can just put all that into a calculator in one go. I'm going to type in 480 multiplied by 0.6, and it gives us 288. Okay. Now in terms of the units, just check. So we've got the centimetres there. We've got grams for the density part, grams per cubic centimetre. So units have got to be that in grams. Okay, and so that's it. That's our mass of this cuboid. Okay. Okay, so the next and final formula I'm going to talk to you about is involving these: pressure, force, and area. Okay. Now you've got a good idea of what I mean by area. Okay. Usually the units are in centimetres squared or in metres squared, and you've probably got a good idea of what I mean by force. Measurements are measured in newtons, by the way, for force, but pressure, what do I mean by that? Okay, well, a pressure is dependent on the amount of force that's been exerted on an object and the amount of area. Okay, so let me just give you a simple example. So my hand, I can use my hand to exert some pressure onto an object, can't I? Okay, so I can actually place my hand there, and at the moment I've just placed it on there, not really exerting much pressure, but if I hold the board this side and I increase the amount of pressure I exert, okay, can you see how I've used that term? I'm exerting a fair amount of pressure, and that's dependent on the amount of force in which I'm using to push my hand against the board, and it's also depending on the amount of area it's taking up as well. Now imagine instead of my hand I use just one finger, okay, and I try and exert the same amount of pressure. Okay, it's very, very difficult. Okay, it's very, very difficult because I can exert more pressure, you see, if I use my whole hand than if I use just one single finger, if I use just one single point. Okay, so the amount of pressure is dependent on the amount of force, in this case my pushing force that I'm using to exert, and the area that comes into contact with the surface. There's a lot more area here, okay, and there's a lot less area here, okay, so it's dependent on both of them. Okay, let me give you another example. Okay, here's my, it's not really a shoe, it's a slipper. Okay, you can't see my feet, so it doesn't really matter what I wear, does it? Okay, I could be in bare feet as far as you're concerned. This is my shoe. Okay, so let me just draw a picture of that. Okay, so here's a terrible looking shoe. I'm not an artist. Okay, now I've got weight, obviously. Okay. But what I mean is I'm exerting some sort of pressure downwards on the floor every time I move around. Here's me sort of moving around. There we go. Every time I move around, I exert pressure on the floor. Imagine I'm walking on top of somebody, okay? They're going to feel the pressure of me walking on top of them, okay? Now, the lighter I am, the less pressure the floor is going to have. The lighter I am, the less pressure someone's going to feel, okay? So imagine I'm walking on somebody. The lighter I am, the less pressure they're going to feel. Does that make sense? Okay? So, in other words, the lighter I am, the less force is being pulled down on me. Force is a product of how much mass I take up and the gravitational constant, G. You're not doing A-level maths yet, so don't worry too much about that. Okay? But the more force that I am exerting downwards because of my weight, which is a product of my mass and gravity, okay, then the more pressure someone's going to feel. Okay. Also, it's dependent upon the amount of area that's being taken up as well. Now imagine I kind of stand on tiptoe. Oh, that's me standing on tiptoe. Okay. Now, what is going to hurt you more? Okay, if someone is walking around you, okay, normally as if they're walking along a pavement, or someone's on tiptoe and they're walking all over you, okay? What if someone tries to stand, here's me, well, trying to stand on just one toe, failed, okay, it's difficult to do that, I'm not a ballerina for crying out loud, okay? Imagine someone is trying to stand on tiptoe on you, you're going to feel that a lot more, aren't you, okay? Now, there's a larger area, a larger surface area, okay, being taken up by someone who is just walking on you with their foot resting flat on you like that, okay? And there's a smaller surface area if someone is kind of like that when they're trying to stand on tiptoe on you, okay? There's a smaller, so that's me trying to indicate there's just one part of my shoe that's standing on top of you, okay? There's a smaller surface area there, okay? And you're going to feel more pressure on the smaller surface area. Experiment if you want. Find the heaviest person in your household and you lie on the floor, ask them to walk over you, okay, and see how much pressure you feel. Whether you feel more pressure when they're walking on you like that, or whether you feel more pressure when they're walking like that, okay? Or maybe you don't, because I don't want you to get them into trouble in case someone has an injury, okay? I'm sure you took that fairly light-heartedly, okay? Well, I hope you did anyway, okay? So can you see that the larger the surface area you have, you're dividing by a larger value. Okay, and if you divide a number by a larger value, you get a smaller answer. Yeah, the larger the number you divide by, the smaller answer you get. Hence, the pressure is going to be smaller. Okay. Conversely, the smaller the area you have, the smaller the number you divide by, the larger your final answer is going to be, the more amount of pressure. I know I went into detail on that, but I just wanted to explain to you how this pressure formula is actually working. Okay, I'm hoping that kind of made sense to you. I'm just going to give you a simple example involving pressure, force and area. Okay, so quite simply, well, I'll tell you what, I'll just take an example from this book here that I've got quite handy. Okay, so I've got a bike pump that's got an area of centimetres squared. The piston of a bike pump's got an area of 7 centimetres squared. So I'll write that in, area equals 7 centimetres squared. Okay, and it says a force of 189 newtons is applied to the piston. So force is equal to 189 newtons. And the question is simply, what is the pressure generated? Okay. What is the pressure generated? So pressure, force divided by area. So pressure is going to be 189 divided by 7. And you can see, because that's in newtons and that's in centimetres squared, my answer is going to be newtons per centimetre squared. Let's just find the calculator and do that division. So 189 divided by 7, and it's 27. Okay, so the pressure generated is 27 newtons per centimetre squared. And that's it. That's all it is. It's as simple as that. As far as you're concerned, in a GCSE exam, you're just going to be able to use this formula in the same way you'd use a formula for speed, distance and time. You don't actually need to know what we mean by pressure, although it does actually help a little bit, if I'm honest. Okay. Well, hoping you found that useful. I'll see you again.